Good evening, guys. How are you? Hope you're doing good. And today we are in the second day of our Visit Marathon series where we are going to learn about the electrical potential and capacitance. So, again, before starting the class, I wish all of you put your attendance in the comment box, in the chat box, and just put a hi to know that you have attended the class. Fine. So, I am seeing some people are putting the attendance. So, I hope you have gone through the video of last class well. And in the last session, in yesterday's session, electric field and charges, I have solved around 15, 16 MCQ questions apart from what I have taught you about all the concepts of electric field and charges. Continuing the same thing, today we'll go to the second chapter. We will learn about electrical potential and capacitance, and also we would be solving a lot of MCQs today, like how we did yesterday. So, without wasting further time, let us start today's lecture. You are in Wisdom Academy and you are watching me. It is Nilesh. So, let us see the first topic of electrical potential and capacitance is about electrical potential. So, we are going to see what is electrical potential. Now, the word electric potential, it is coming from the place which determines the flow of charges, where the charge is flowing. So suppose I have a water in a pipe, and if the water is flowing on the right hand side, if the water flows on the right hand side, then I can say that the left side has a higher potential than the right. Are you able to feel what I'm trying to say? Suppose I have a pipe and I am seeing that water is flowing in this direction. If I am knowing this is only possible if the point A is at a higher potential and if point B is at a lower potential. So to flow the water, point A should be at higher potential, point B should be at lower potential. Same way, if the charge wants to move from higher potential to, from one point to another point, the point from where it is moving must be at higher potential, and the point to where it is moving must be at lower potential. The first thing what I told you about electrical potential is it is the property which determines, it is the property which determines the direction of flow of charge. The direction of flow of charge. So, if you want the exact technical definition of what is electrical potential, I would say it is the work done. It is the work done in moving a unit positive charge. It is the work done in moving a unit positive charge from infinite to the point where you want to place it. For example, if you want to bring a charge from somewhere and put it here, a positive charge, then how much work you are doing to bring this charge from somewhere infinite to this point is known as the electrical potential. This is I'm telling mathematically. So V, electrical potential, is represented by a capital letter V, and V is equal to work done per unit charge. So I just told you very basic thing about electrical potential. It is the work done to bring a unit positive test charge. If you ask me, sir, can I take negative? Definitely you can take negative. There is nothing wrong in that. It is just the convention. It says that it is the work done in bringing a unit positive charge from some infinite position to the position where you want it to be there. This is about the electrical potential. Let us see some very basic question which has been asked in the examination in the past from this electrical potential topic. How much work is required to carry a 6 coulomb charge from negative to the positive terminal of a 9-volt battery? So see, this question not only teaches you one sum, but rather it also teaches you some concept. See what concept it is teaching. First, you see the terminal of the potential, terminal of the battery. It is saying how much work is required to carry a 6 coulomb of charge from the negative terminal to the positive terminal. I hope by now you know that negative terminal is at lower potential, positive it is at higher potential. So any charge will go from higher potential to lower potential. It can go by itself without any external force. You know this? A charge can move from higher potential to lower potential without any external work. That is how the things go. If there is a slanting surface, you keep a ball there without you push or give any force to it, it will fall down by itself because it is at the point of higher potential compared to the lower potential point. But the challenge is how the charge travels from this negative terminal to the positive terminal. That is what the concept is, and that's how the battery is used. So battery has some chemical energy, right? Battery inside it has some chemical energy, and this chemical energy is only responsible to make the charges move from a point of lower potential to a point of higher potential. So in this question they're asking you that how much work is done. So by this question you're learning this concept also, that how a battery work, a battery or a cell, it makes the charge move from area of lower potential to higher potential, because higher to lower it will move by itself, right? So we know the formula of electric potential V, which is equal to work done per unit charge, and we can find the value of work done from here very easily. Work done will be equal to potential into charge. Now what is potential? Potential is given as 9 volt and charge is given as 6, so it is 54 joules. Okay, there is no option given like that, so maybe there is a mistake. This will be 6 microcoulomb. This should be 6 microcoulomb. If it is 6 microcoulomb, then it will become 54 in 10 power minus 6 joules, isn't it? So maybe they have missed that micro sign here. So the answer will be 54 10 to the power minus 6 joule if the charge is 6 microcoulomb, not coulomb, right? I hope I am clear. Next topic. So after this, we have electrical potential difference. See, potential difference and potential, they are not same. They are similar. They have some difference inside. Listen to me very carefully, you will understand the difference. I said electrical potential was the work done per unit charge, because it was work done by the Q. So it was the work done per unit charge to move it from infinite to one point, right? Electrical potential difference would be in any circuit. If you want to move a charge from one point to another point, then that is known as potential difference. So suppose, what is the potential here? What is the potential here? That is point A, point B, VA and VB. So what is the potential difference between them? We'll only decide whether it will go from A to B or B to A. If it is going from A to B, I will write potential difference delta V is equal to VA minus VB. If it is going from B to A, I will write delta V is equal to VB minus VA. I hope you are understanding what I'm trying to say. So potential difference is the work done to move it, work done per unit charge to move it from one point to another point in a circuit, right? So potential difference is always told, this electrical potential difference is always told between any 2 points only, between any 2 points. We will not use the word potential difference for a single point. Electrical potential can be used for a single point. What is the electrical potential at that point? So that will be how much work you have to do to bring a charge from infinite to that point. But when I am saying potential difference, it is the work done. Before coming to work done, it is always told between any 2 points only. Between any 2 points in some electric field. Between any 2 points in electric field, electrical potential difference between any 2 points in electric field is, what is this? It is the work done. It is the work done to move, or I should say work done per unit charge. Work done per unit charge to move it from one point to another. One point to another in presence of some field or in presence of electrostatic forces. Electrostatic forces. So I hope you are understanding the difference between electrical potential and electrical potential difference. Again, I will repeat, electrical potential is for a point, how much work you are doing to bring a charge from infinite to that point, and electrical potential difference between any 2 points, for any 2 points, is the work done per unit charge to move it from one point to another point. If you ask me, so what is the mathematical definition? Yeah, delta V, that is the potential difference, that can even be VB minus VA, or it can be VA minus VB also, and that will be equal to work done per unit charge. So definition wise, sorry, it is almost same as the electrical potential, but concept wise it is little different. So both of them have same units, whether it is electrical potential or potential difference, they will have unit as volt, and they both are scalar quantities. So that is about electrical potential difference. Let us go to the next topic, which is electrical potential due to a point charge. So now we know electrical potential is sorry, work done per unit charge. Now I want to find what is the electrical potential to a single point charge. So if I have a point charge like this, and I want to find what is the electrical potential due to this point. V at any distance, suppose at a distance r, what is the potential here? If I'm writing it as A, what is the potential at A, which is r distance away from this charge? So that I can find, and that will be equal to K into Q by R. Remember this. Already we have derived this. That is how this has come. I hope you can remember. Potential, electrical potential is work done per unit charge, and work done is force into displacement, and then it is Q. And force formula, you know, it is K into Q1 into Q2 by R square. Already one distance is here R, and on Q is there. This Q will get cancelled and this R will get cancelled, and you will get KQ by R. This is how it has come. So you should remember that electrical potential at any point is KQ by R. So due to any charge at any distance. So if I have 5 coulomb charge, for this plus 5 coulomb charge at a distance of 5 meter, what would be the potential I can find? It will be K into 5 by 5. That's all. That is the electrical potential. That much volt is the electrical potential. That is, that much work done per unit charge is required to move, to bring any charge from infinite to this point 5 meter away from 5 coulomb charge. I hope you are getting my point. That is for a single charge. If you have multiple charges, system of charges you have, then obviously if I have one charge here, another charge here, another charge here, another charge here, here, and I want to find due to all these charges what is the potential at this point. Let me take it as x. So at x, by all these 5 charges, I can write it as, to be more precise, plus q plus 2q minus 3q plus 5q minus q. For all these charges, what is the electrical potential? I can find. See, they will have their own distances. Suppose this is R1, this is R2, this is R3, and this is R4, and this is R5. So obviously, V net, overall V at X, that will be equal to potential due to first plus due to second, due to third, due to fourth, and due to, actually I have taken 5 here, so due to fifth. One good thing is it is not vector addition. Like electric field, electric force, they are vector quantities. So when you want to add the net electric field or electric force would be the vector addition of all those individual things. Here, it is a scalar addition, algebraic addition. So if you find, it will be K Q1, that is equal to whatever the value is. In this case, I have taken it to be, I think R1, I took it to be plus 2Q. So K into plus 2Q. I will just write KQ1 by R1 plus KQ2 by R2, something like that, till KQN by Rn. So when you want to find the electric potential for a lot of points, I mean a lot of charges due to a single point, you can find it by this vector addition of individual potentials. As simple as it is. Let us take a question now based upon all these things. So if you see 4 point charges minus q, I mean, that is minus capital Q, minus small q, 2q and 2 capital Q are placed one at each corner of the square. The relation between capital Q and small q, for which the potential at the center of the square is 0. So a simple question, you just need to draw a square first. Let me draw a square, and if there is a square, I have 4 point charges. So let me start with this minus q here, then minus q here, then 2q here, and 2q here. 4 charges. And they are saying that at the center, the potential is 0. V is equal to 0 at the center. You must know what are the distance of this, of this, of this, and of this. Yeah, you can find very easily. If it is square, it will be a or x or whatever you want to take. If this is a, this will be a, a, and this will be a. So the whole length will be root over a square plus a square. That will be equal to root 2a square. And then if you divide by 2, it will be a by root 2, I think. So a by root 2, this whole distance would be equal to root over a square plus a square. That will be equal to root 2 into a. And then half of this, that is this distance up to O, it will be 1 by 2 times of root 2a. Yeah, obviously a by root 2. So when I got the distance, now if I want to find what is the potential, what is the relationship between them, then at VO, it will be V1 plus V2 plus V3 plus V4. And we know V at O is 0. So 0 is equal to, the first thing will be equal to K into minus Q, K into minus Q by A by root 2 plus second K into this minus Q by A by root 2 again plus K into 2Q by A by root 2 and again K into capital 2Q by A by root 2. So A by root 2 can be taken common and it will go, and that side will become 0 anyhow. So I am going to get 0 is equal to K also can be taken out and it will become 0. So I will be remaining with minus Q plus 2Q and plus 2Q. So if you add the respective quantities, I will have minus Q and plus Q as Q, and again minus 2 and QQ as plus Q. That is equal to 0. So obviously Q is equal to minus Q. So this is the answer. For this question, capital Q will be equal to minus Q. I hope you have understood. A very basic question. The only thing is you should know the formula of superposition. If there are more than one charge, then you have to use the addition of all the respective electric potentials. Let's go to the next question. 3 charges, 2Q, minus Q, and minus Q, lie at the vertices of a triangle. The value of E and V at the centroid of triangle will be how much? See, this question is from Cbse sample paper. This year, 21-22 sample paper. So this kind of questions you can expect. I'm trying to say that. This kind of questions can be expected in the examination, board examination. So if I take this triangle, this is suppose 2Q, this is minus Q, and this is minus Q. And since they have told centroid, definitely this distance, if I'm taking it as R, this will also be R, and this will also be R, equidistant from all the vertices. So they have told that they asked you to find at this point, if I take it as O, what is the electric field at O and what is the electrical potential at O. Electric potential we will find, that is very easy to find. We will just do the scalar addition. So V at O will be equal to V due to first point plus V second charge plus V due to third charge. That will be equal to K. First, if I take this, it will be 2Q by R plus K minus Q by R plus K into once again minus Q by R. So if I am able to see, minus Q will become minus 2Q. So this will get cancelled and finally we will get 0. So one thing is sure, V is equal to 0. That is V at this point is 0. So this option and this option are ruled out. So definitely A and D cannot be there, 50-50. Now I have only B and C. So let us try to find whether electric field will be 0 or not. Again, from yesterday's class, yesterday's concept. At this point, if I bring a unit positive charge for checking the electric field, it will have an attractive, I'm using some other color. Yeah, it will have some electric field in this direction, isn't it? This again it will have in this direction, and this 2q will have a repulsive force in this direction, isn't it? Very clear. If I keep a unit positive charge q here, then due to minus q, attractive field, due to minus q, attractive field, due to this 2q, repulsive field. Now this minus q and minus q field, it will be definitely in this direction only or somewhere in this direction only. There is no question that electric field can be zero. Only if it would have in the opposite direction, there is a chance of E being zero. But since all the forces are acting in the same direction, how it can be zero? So electric field definitely cannot be zero. This option also is ruled out. The correct answer is C. That is, electric field is not zero, but electric potential is zero. See, very simple question. Again, I'm said you. Very simple question, which was there in the sample paper. Only if you have very much good clarity about electric potential and electric field, you can solve this. Let us go to the next topic, that is relation between electric field and electric potential. I have a lot of times seen questions, not only this year, but many other years, coming based upon the concept of electric field and electric potential. So you must know the relationship is the relationship between electric field, that is E, and electric potential, that is V, is that electric field is negative gradient minus dV by dr, negative gradient of the electric potential. Now, see, electric potential is scalar, but electric potential gradient is not scalar, it becomes vector quantity. I will write somewhere, very important point, please note it. It's very important point that electric potential is scalar, it is a scalar quantity, but electrical potential gradient is vector, because electrical potential gradient becomes electric field, isn't it? See, negative potential of negative gradient of electric potential, it becomes electric field. So potential gradient is a vector quantity, only electrical potential is a scalar quantity. Okay, so now by this formula, one thing we can find, if you remember the yesterday's session, if you have a spherical, actually this topic was not there in the syllabus, but anyhow I'm going to tell you that if you have a spherical shell and you want to find what is the electric potential at this point A, some x distance outside, at the surface of this spherical sphere, that is definitely capital R, that is radius, and at some other position y inside the sphere, let it make C, it is a distance of y. So point A is at a distance of x from the center, point B distance of r from the center, and point C at a distance of y from the center. If you find the respective values of electric field at A, you will get just by the formula K Q by x square. You find electric field at B, that will become equal to K Q by r square. And if you find electric field at C, that will be K Q by y square, isn't it? Is it so? Definitely not. It will be zero. Just yesterday I have studied by the Gauss law that electric field would be present only if the charge is enclosed. If charge lies somewhere here, it is not lying here, definitely it is not going to have any electric field, because the charge enclosed must be equal to zero. If I'm talking about charged spherical shell, charge is somewhere here. Are you getting my point? So if I want to find the electric field at A, I'll draw a Gaussian surface at A, and definitely charge is enclosed. That's why I got KQ by x square. If I draw at B, definitely charge is there. But at C, if I draw a Gaussian surface, no charge is enclosed. If charge itself is outside, it will not have electric field. We have learned it in the last class. So if you see about the potential, electric potential at A, that will be equal to K into Q by R, that is x in this case. Electric potential at B, obviously it will be K into Q by R, and electric potential at C, will it be zero? No. Why it not be zero? because electric potential is not governed by the Gauss law. See here, electric potential from here, E is equal to minus dV by dr. So if electric field is 0, this must be a constant, isn't it? Because d by dx of a constant only is 0. If V is a constant, only electric field can be 0 inside. V is a constant means after this surface, everywhere V is constant. So it will remain same as K into Q by R. If I draw and tell you the same thing in the graphical form, remember that if I'm drawing a graph for electrical potential, this is the radius, that is, in this case I'm taking it as radius, and this is the electric field. So if I draw about electric field up to the point when the radius r is equal to r, there is no value of electric field, and it has a value only at this point, maximum value, and further when the radius will increase, it will keep on reducing. Why it will keep on reducing? Because it is inversely proportional to distance. Distance increases, E will decrease. But if I take the graph of potential, that will be not the same, because it will have same value. If I'm drawing about V now, it will have same value up to this point, and then it will decrease. So it is also inversely proportional to R only. V is inversely proportional to R. As the R will increase, the V will decrease. But up to this radius, it will remain constant. Reason is this: the relationship between electric field and electric potential. If V is constant, electric field is 0, and that is why the electric potential is constant up to R and then starts to reduce. This is the relationship between electric field and electric potential. If I go to the next page, we have a question. If a potential in a region is expressed as xyz, 6xy minus y plus 2yz. So I have the value of V given as 6xy minus y plus 2yz. This is the value of V. Now what they are asking you? They are asking you to find the electric field at a point 1, 1, 0. Very good question again. It can be solved only if you know the concept of the relationship between V and E. So I just now told you that E is equal to minus dV by dr. What we will do, based upon we have three things here, x, y, z, all three coordinates are there. So first you must find what is the value of Ex. That will be equal to minus dV by dx. And if I differentiate this function with respect to x, what I'm going to get, you see, that will be equal to minus 6y, and nothing else. This two terms will become 0 because there's no x coefficient there. Same way, when I find E, electric field at y, that will be equal to minus dV by dy, and that will be equal to, the first term will become minus 6x, and again the second term will become plus 1, isn't it? And third term will become minus 2 z. I hope you're understanding this. So minus d by dy of v. So v is 6xy. So my d by dy of 6xy will be 6x. Minus there, so I put minus 6x. Again, d by dy of minus y will be equal to 1. So I have put minus here. So minus and minus will become plus. So minus 1 and minus 1 will become plus 1. And again, plus 2yz. So it will become 2z. Since minus there, it will become minus 2z. Same way, if I do for z, it will become minus dv by dz, and that is equal to, first term, second more z is there, so minus 2y. So this is the electric field at x coordinate, y coordinate, z coordinate. Now net electric field, which will be equal to Ex plus Ey plus Ez, would be equal to, see, minus 6y minus 6x plus 1 minus 2z minus 2y. I added all these three. This is the value of net electric field. And they have given you a point at 1, 1, 0. So if I put the point as 1, 1, 0, then you will get an idea about what would be the value of the coordinates. So I hope you are understanding what I'm doing. First, I found the Ex, that is dv by minus dv by dx, and I found this. Then I found Ey minus dv by dy. I found the value. Then I found Ez, this thing, and then I wrote it in terms of this thing: minus 6y minus 6x plus 1 minus 2z minus 2y. Then if I just find what is the I cap, I mean, what is the value of point 1 comma 1 comma 0? That is x is equal to 1, y is equal to 1, and z is equal to 0. You put that, see, this thing is with I cap. So I should write like this: I cap, and this full term is j cap, and this term is in k cap, isn't it? I forgot to mention here I cap, j cap, and k cap. So when I put the coordinates, see, y is 1, so it will become minus 6. So it will become minus 6 I cap. Okay, minus this term. X is how much? 1. So 6 plus 1 minus z is 0. So, yeah, minus 0. This much j cap, and minus y is 1. So minus 2 k cap. So when I solve this, I'll be getting minus 6 I cap. If I take minus outside, 6 I cap plus 5 j cap plus 2 k cap. So I think this is the answer. So see, again, a very simple question, I would say. It's not that complex question, but the only thing is, only if you're having an idea about the relationship between electric field and electric potential, you can proceed in this question, or else you will struggle. Let us go to the next page. Okay, one more question is there. The electric potential at the center of the sphere, if the hollow metallic sphere of radius 10 centimeter is charged such that the potential of its surface is 70 volt. Obviously, if you have a metallic sphere and its potential is 70 volt at the surface, in center also it will have same 70 volt, because just now I have taught you, we have learned that electric potential does not change as you go inside. If I ask you what is the potential at this point, it will be definitely less reduced, but it will be constant throughout this sphere. I said no, it will not change. So the correct answer will be 70 volt. Simple question. Let us go to the next point. Electric potential due to electric dipole. So in the last class, we have last class means yesterday's session, we have learned about what is the electric field due to electric dipole at an axial point, at equatorial point. Same way, for a dipole, we can even find the electric potential. Suppose this is minus q plus q. Dipole means 2d distance apart from the center. Take x distance away, a point, let it be P, and you want to find what is the dipole. I mean, what is the electric potential at point P? I want to find what is the electric potential at point, that is axial point. Then when you solve this, and find, you will get the value as K into P by x square minus d square. This is the concept. Kp by x square minus d square. And obviously, if d is very much less than x, then V axial will become equal to Kp by x square. Kp by x square, because d will not be there. So this is the formula. See, electric field was Kp by x cube. Actually, for axial it was K into 2p by x cube. Here it is Kp by x square. Don't confuse, it is square, there it was cube. And if you find for equatorial point, no, it will be 0. You can just check your notes, it will be 0. So electric potential due to a dipole at an axial point is Kp by x square minus d square, and due to, at the equatorial point, due to this dipole is 0. I hope you have understood this. Let us go to the next page. What is equipotential surfaces? As the name says, if on a surface all the points have same potential, it is called as equipotential surfaces. So for various different charge conditions, you should know what is the shape of the equipotential surface. For example, if I ask you for a point charge, what will be the surface, negative or positive, whatever. If it is positive, it will be radially outwards. I'm talking about the electric field. So like this, and you connect all these points. See, it is not circle. I'm saying radially outwards, all directions coming out. So it will be a sphere. So the shape of the equipotential surface will be a sphere. Suppose you have electric field like this from two charged plates, that is uniform electric field, parallel straight lines. Then obviously it will be like this, sheets. This is the equipotential surface. Again, this is the surface. So it will be plane sheets. Plane sheets. If it is like that, we have also seen sometimes if electric field is converging like this in this direction. So the electric, if you take all the points, it will be like this. The electric, I mean equipotential surface. It can have all these shapes. So if I have a straight wire like this, that is, it will produce something like this in all the directions, radially outward direction, everywhere it will produce like this. I mean the electric field. So potential will be a cylindrical surface, isn't it? I mean equipotential surface. So equipotential surface will be the concentric cylinders here, like this, concentric cylinders. So equipotential surface, for various conditions you should remember, and it is just a surface which has same potential at all the points. Important thing is the properties of equipotential surface, a very important thing, very very important, because from all these properties, like how in the last class we studied about the properties of charge, same way properties of electric lines of force, they are very important concepts. Same way we have properties of equipotential surfaces here. So please pay attention. I'll write one by one all the properties. But the first property of the equipotential surface is that if you move a charge from one point to another point on this surface, on the equipotential surface, the work done will be zero. So there is no work done. There is no work done in moving a charge in, along the equipotential surface. So anywhere along the equipotential surface, if you move here, 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 anywhere you keep on a particular surface, I'm not talking about moving a surface from one place to another place. If you have a particular surface only, work done will be zero if you move a charge. If you move from one surface to another surface, definitely work will be done. I hope you're getting my point. The second important property is that electric field is always perpendicular to the equipotential surface. Remember that. So if I have equipotential surface like this, then electric field will be always perpendicular on this surface. I hope you're understanding this. So electric field is always perpendicular to the equipotential surface. You can have questions from this. The conceptual questions can come from this simple statement also. The third property can be that we know that electric field is negative gradient of potential. So from here you can understand that for any particular surface, V is going to be constant. So please pay attention. This dv, if it is constant, that is, there is no change in potential at any particular surface, then I can write that E is inversely proportional to dr. You know what is the meaning of this? Meaning is that if electric field is higher, the closeness of dr means distance between two surface, it will be lower. If we have surfaces like this very very close to each other, it means electric field is very high. If they have more space between them, electric field is lower. I hope you're understanding this. Since the change in the potential is a constant, there is no change in potential, therefore electric field is inversely proportional to dr. So if the dr is less, electric field is high, means closeness of the equipotential surface gives us the idea about the strength of electric field. I hope you are understanding this. The more close the equipotential surfaces are, the more higher the electric field is, or the more stronger the electric field is. Right. So let us go to the next important property of equipotential surface. that no equipotential surface can ever intersect. Two equipotential surface cannot intersect. Cannot intersect. Obviously, of the same charge. You cannot bring two different charges and they may intersect. And for a single charge or for a single system, all the surface will always be different. They will not intersect with each other. The next thing is, we know very well that electric potential is scalar. I told this point already. So electric potential is scalar, but this dV by dr, that is electrical potential gradient, is vector. I hope you know why. Because dV by dr represents electric field. One more thing. From this point itself, I can take one more thing. That is E is equal to minus dV by dr is there, no? It says that rate of change of potential with the distance is always against the electric field. This negative sign is showing that, I will write the point here, that rate of change of electric potential is always against the electric field. So electric field direction, I mean, it will be such in such a way that the electric field is, I suppose, I'm having electric potential increasing in this direction. So electric field will reduce in that direction. So suppose electric potential is going in this direction, it means electric field is reducing, if you go for it. I hope you're understanding this. So electric potential is, that is the rate of change of electric potential is always against the electric field. These are some very important properties of the equipotential surface, and from this property itself you can expect some questions. Let us see if any question is there. Yeah, I have taken a question. Equipotential surface associated with an electric field which is increasing in magnitude along the x direction. See, again a simple question. So if I am talking about any surface with an electric field which is increasing along the x direction, see, if you draw a coordinate axis with x, y and z, if it is increasing in this direction, definitely it must be, that is they are asking you, increasing in magnitude along x direction are planes parallel to yz plane, planes parallel to xy plane, coaxial cylinder of increasing radii, or planes parallel to xz plane. If it is proceeding in this direction, it must be in the yz plane, isn't it? So the answer is planes parallel to yz plane. I just not told you. So if suppose it is proceeding in the y direction, then it will be plane in the xz plane, isn't it? If it is going in y direction, it will be yz plane. Sorry, yx plane, xy plane. This will be xy plane. This will be xz plane. Here I have yz plane. So just by knowing the direction of the electric field, you can just determine, or the direction of electric potential, you can determine that what direction it is linked with. I hope you're understanding this. So if I go to the next question, work done in moving a unit positive charge through a distance of x meter on an equipotential surface. So very simple question. When they have mentioned that it is on a particular equipotential surface, without even thinking twice, you can take it as 0, because as I told you, there is no work done in moving the charge on the same equipotential surface. See, very simple questions they are asking, but only if you have the knowledge about the basic things, you can attend the question itself, or else you'll confuse what is this work done. It will be something like some x square joule will be there, so that kind of confusions will come. Simple question this is. Let us proceed. Electric potential energy. Okay, so now we have learned about electric potential. Electric potential and electric potential energy is different only by one small thing. Electric potential was work done per unit charge. Electric potential energy is just the work done, that is work done to move a charge from one point to another. So see, very similar to the electric potential, but that was work done per unit charge. It is just work done. So we know already that V is equal to W, work done per unit charge. So this work done, that is, will be equal to Q into V, that is U. So electric potential energy will be equal to Q into V. Electric potential energy U will be equal to Q into V. Very important thing, remember this. And also, one more thing I'll tell you, if you see Q into V, already V was KQ by R, so it will become equal to K into Q1 into Q2 by R. So, if I tell you that in this two chapters, what I studied from they studied from today, lot of things we studied. We studied electrostatic potential, that is the electrostatic force, F was equal to K Q1 Q2 by R. Electric field was K Q by R square. It's R square. Today we have studied electric potential is K Q by R, and electric potential energy U is K Q1 Q2 by R. Almost all the combinations we have seen. Never confuse in all these four. Electric force is KQ1 Q2 by R square by Coulomb's law. Electric field KQ by R square. Electric potential KQ by R, and electric potential energy is KQ1 Q2 by R. Right. So let us go to the next page. One question is there. If an electron is brought towards another electron, the electric potential energy of system, what happens to it? So see, if the electron is brought towards another electron, one electron is already present, you're bringing another electron towards it. Definitely it will have a repulsive force. Do you agree with me? The force will be very repulsive. If the force is repulsive and still you want to bring it, something is opposing but you're still pushing it, what will happen? Too much work will be done. And what work you are doing to push it near this electron, that will make its potential energy to increase. Obviously. So the answer is increases. I hope you're understanding this. Simple. So if I go to the next topic, that is work done on a dipole in uniform electric field, right? So we know that what is a dipole, and we very well know what happens to dipole when it is placed in the uniform electric field. So if you have dipole kept in the uniform electric field like this, it will acted upon by a torque. I hope you remember that. And that torque will make it to rotate. If it is asked that how much work is done on a dipole, you can find the work done. We know that tau is equal to Pe sine theta. So work done will be equal to force into displacement. That work done will be equal in this case as force is torque. So displacement will be in theta, tau d theta, isn't it? So since I am doing d theta, it will be small work done, dw it will be. So it will be dw. So total work done dw will be equal to integration of tau d theta from theta 1 to theta 2, isn't it? That will be equal to how much? Please see from here. It will be P E sine theta d theta from theta 1 to theta 2. So when you integrate, what is integration of sine theta? I hope you know, minus cos theta. So it will become equal to minus Pe cos theta limits from theta 1 to theta 2. So when I put the upper limit minus lower limit, it will become minus Pe cos theta 2 minus cos theta 1. So if I bring minus inside, I will get the work done, U or whatever you want to write, W, work done, that will be equal to Pe. If I take negative inside, it will become cos theta 1 minus cos theta 2. This is the work done on a dipole in a uniform electric field. On a uniform electric field, it is Pe cos theta 1 minus cos theta 2. Yeah, if I assume that theta 1 is already, the dipole is already at 90 degree, and then I am moving it. That is, if I take theta 1 as 90 degree and theta 2 as some value theta, whatever angle I am moving, sub 2, 3, 4, 5 degrees, then I can write from here that work done will be equal to Pe cos 90 will be 0, and cos minus cos theta will become minus cos theta. So it will become minus Pe cos theta. So if you are trying to move a particular dipole from this position, that is 90 degree, to some angle like this, then it will have the value as minus Pe cos theta. So I hope you're clear in the concept of work done. Let us see one question based upon it. So work done on a dipole. Electric dipole of moment P is placed parallel to the uniform electric field. So the electric dipole is placed at parallel, not perpendicular. So remember, minus P cos theta is only for a dipole placed perpendicular. Now dipole is placed like this, minus Q plus Q. Right, amount of work done in rotating the dipole by 90 degrees. So they're asking to rotate from here to this position, 90 degree. Yeah, we can do it. So what will happen? We have the formula U is equal to PE cos theta 1 minus cos theta 2. So from where to where they're asking? They're asking from 0 to 90. So theta 1 is 0 here and theta 2 is 90 here, nothing else. So put cos, it will become PE cos 0, that is cos 0 minus cos 90. So cos 0 is 1 and cos 90 is 0. So it will become equal to plus PE. So the answer will be PE. I hope you're clear. Simple question. Let us go to the next part. So then we have behavior of conductors in electric field. So now learning about this potential energy, work and all these things, we have come to the second part of this chapter about that conductors and capacitance. Let us try to learn what is the behavior of a conductor if you're keeping it inside an electric field. So suppose I have electric field like this. Obviously, it will be due to some positive charge and negative charge. And inside this electric field, uniform electric field, if I am placing a conductor like that, obviously conductor will have some free electrons. So that free electrons will be attracted by the positive terminal and all the protons sorry, will be attracted towards the right. So when it happens, if all the electrons are on one side, protons are on one side, you can see very clearly there will be an electric field coming inside this itself, but in the opposite direction like this. I hope you're able to see. So now what will happen? The electric field is coming in the opposite direction. It will cancel the electric field, external electric field, and the net electric field inside the conductor, how much it will become? It will become 0. So remember that conductors, they don't have any electric field inside it, right? But outside the electric field, no, outside the conductor, I should say, outside the conductor, electric field will be there and electric field will be perpendicular to its surface. Here it will be in this direction, here it will be in this direction. So outside the conductor, electric field is perpendicular to the surface. See the very small points, but these points may play a role in one question in the examination. So remember these things. Another point is, I mean, this charge is there, no? It always stays on the surface. It will never go inside this conductor. So it will stay on the surface and the electric field will be perpendicular to the surface. This is how the conductor behaves if you're keeping it inside the electric field. Now the next important topic, that is electrical capacitance. So when I'm saying capacitance means capacity to store energy. So it is the ability, capacitance is the ability of any capacitor. Some books will even write condenser. Some books will even write conductor. So it is the ability of a capacitor or a conductor or a condenser, whatever you say, to store energy. That is the capacitance, electrical capacitance. So obviously, to do that, we are giving more and more potential. So the more potential you give, the more charge it develops. So Q is proportional to V. The increase in the potential will lead to increase in the charges. So Q is equal to CV. And this C is called as capacitance, which is equal to Q by V. Its SI unit is farad. The SI unit of capacitance is FARAD, that is farad. Obviously, it will be joule per volt. That is called as farad. Now, let us try to learn what is the capacitance of a spherical capacitor. If you have a spherical capacitor like this, and I want to find what is its capacitance, what is the capacitance of a spherical capacitor, then it is very simple. It is 4 pi epsilon naught r. R in this case I have taken small r, so you can take small r or capital R, whatever you want to take. So r is the radius of the sphere. So capacitance of a spherical capacitor is 4 pi epsilon naught r. And if you take earth, for earth, if you try to find what is the value of capacitance, you will get the answer as approximately 711 farad. Sorry, microfarad. 711 microfarad. So imagine that earth itself is having this much small capacitance. That's why whenever we are learning about the capacitance, we'll always take nano farad or microfarad, or milli. When milli will not take, micro and nano only will take more. So it is that much small unit. So 1 farad is a very big quantity. 1 farad is a very, very big quantity. Let's come to question number 10. This question, it's saying that 64 water drops having equal charges combined to form one bigger drop. The capacitance of bigger drop as compared to that of the smaller drop, they're asking you. Whenever these kind of questions are there, these many things are combined to form one thing, especially drops. In this chapter, you will have this kind of question. First thing you find the relationship between the small radius and big radius. That can be found just by knowing the volume. So volume will not change. So volume of the big drop will be equal to volume of the small drop into 64, obviously. Total volume will not change. So for big drop, it is 4 by 3 pi r cube, and it will be 64 into 4 by 3 pi r cube. This will get cancelled, and you will have r by r, the whole cube, is equal to 64. So r will become equal to 4r. So understand that the capital R is 4 times the smaller r. Capital R is 4 times the smaller r. That is the relationship. Now they're asking to compare the capacitance. So capacitance of bigger drop divided by capacitance of smaller drop. So bigger drop, it is 4 pi epsilon naught r, and smaller drop, it is 4 pi epsilon naught small r. Capital R is 4r. So 4, everything will get cancelled. 4r by r, that is 4. So it will become 4 times. So capacitance of bigger drop will be 4 times the capacitance of smaller drop. Next is capacitance of spherical. If the diameter of Earth is 128 into 10 to the power minus 2 kilometer, what is the capacitance of the Earth? This you can find. Actually, you can find because C is equal to 4 pi epsilon naught r. So 4 pi epsilon naught will be equal to 1 by 9 into 10 to the power 9. And r of the Earth has been given as, this by 2. So 128 by 2 will be equal to 64 into 10 to the power 2 kilometers, or 10 to the power 3 meters. So when you solve this much farad, or you will get the answer as 711 microfarad. I just now told you. You can remember this value itself because questions are asked from this topic. So the capacitance of the Earth is 711 microfarad. So next comes the principle of capacitance. Don't think I'm going fast, but I want you not to wait for long. That's why I'm going in a pace what is required. So principle of capacitance. Right. So you know very well by now that capacitors are used to store charges. So principle will definitely be to store more and more charge. Now, how can capacitance increase? See, a simple thing I'll tell you. If I have a charged plate, it is positively charged plate. and it is brought near to a neutral plate. What would happen? If there's a neutral plate, it will have some negative accumulation of charges on this side, and this side it will have positive accumulation of charges. Net charge will be same, but negative will go on one side, positive will come towards other side. Now there is no change. But suppose all these positive charge I am taking out somehow by earth. By earthing in, I am taking out all the positive charge. Then what will happen? Only negative will remain. So total positive minus this negative will reduce the charges. So now you see, we know that Q is equal to CV, isn't it? And C is equal to Q by V. So if the potential reduces, the capacitance will increase. That is the principle of capacitance. Very simple. So suppose if I have here V1, and if suppose V1 for this surface V2, and this surface V3, and V4 was there. So initially anyhow V3, V4 will be equal, that will have no effect. But now when V4 become equal to 0, the net potential will be equal to V1 plus V2 minus V3, isn't it? So if all are assumed to be same, if suppose V1 is equal to V, V2 is equal to V, V3 also is equal to V, so it will become V plus V minus V. So initially it was 2V and now it became 1V. Its potential reduced. So if potential will reduce, the capacitance will increase. That's the concept of capacitor. We can either increase the charge or we can reduce the potential to increase the capacitance. So what is the capacitance of a parallel plate capacitor? So if you have a parallel plate capacitor like this, there are two parallel plates, and if you want to find what is the capacitance of that, so one plate will be positively charged plate and there will be negatively charged plate. Already we have seen its capacitance will be equal to epsilon naught A by D. Remember, it's very simple. Epsilon naught A by D. I can assure you in the board examination, you will definitely have questions from capacitance. Believe me, you will definitely have question from capacitance, and mostly from parallel plate capacitor only. See, I'm not guessing the question. I don't know it, but I'm just assuming. I'm just, by my experience, I'm telling you, questions can come from parallel plate capacitor in the board examination, right? So we can see very clearly from here that for a parallel plate capacitor, C is proportional to area of the plates and inversely proportional to distance between the plates. So more is the area of plate, more is the capacitance. Less is the distance between the plates, more is the capacitance. That is the concept. So let us take one question. Yeah, one assertion and reasoning question. So the force between the plates of a parallel plate capacitor is proportional to charge on it. Okay. Electric force is equal to charge per unit area. So we know very well that F is equal to QE, right? Electric field, E is equal to F by Q. So the force between the plate is proportional to the charge is actually correct. If electric field is constant, F is proportional to Q, no doubt in that. Q will increase, force will increase. So assertion is true. Second thing is electric force is equal to charge per unit area. Electric force is equal to charge per unit area. Where? No way. Q by A is called as sigma. That is charge density. Linear charge, aerial charge density. Area charge density or surface charge density is only Q by A. So this is wrong. So A is true, but R is false. I hope it is clear. So if I go to the next page, yeah. So combination of capacitors in series and parallel. So you know very well that capacitors can be made in series or parallel. If it is in series like this, having capacitance of C1, C2 and C3, and if it is applied to some potential, remember that the charge remains same, charge will not change, it will have same charge. What will change is the potential. It will have V1, it will have V2 and it will have V3. So net V will be equal to V1 plus V2 plus V3, and when you solve, V is equal to Q by C, so Q by C1 plus Q by C2 plus Q by C3. Finally, you get 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So if you have capacitors connected in series, the net capacitance is found by 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Right? What you have to remember is, in the series combination, charge remains same, potential changes. Similarly, if you have a parallel combination like this, you will have capacitor here, some capacitor here, and some capacitor here with capacitance C1, C2, and C3. Obviously, here the potential will remain same. It will have same V, but Q will divide itself as Q1, Q2, and Q3. If you find at the end, you will get C parallel is equal to C1 plus C2 plus C3. So net capacitance will be the summation of three capacitances, exactly opposite of what we have seen in the resistances. Resistances, if it is in parallel, it will be 1 by R is equal to 1 by R plus 1 by R2 plus 1 by R3. Here, if it is in parallel, the C is equal to C1 plus C2 plus C3. Next is energy stored in the capacitor. That also you must know by now, that energy stored in the capacitor, the formula U is equal to Q square by 2C, Q square by 2C, or half CV square, half CV square, or half QV, whatever you want to remember, half QV. So all these things are the formula of energy stored in the capacitor, Q square by 2C, or half CV square, or CV square by 2, or QV by 2, whatever you want to say. All these are the formula of energy stored in the capacitor denoted by U. Next you have energy density. See, this concept, I don't know how many of you are knowing this, but it is very common concept. I have seen the questions coming from this area very commonly in the examination. So please pay attention if you don't know much about it. So what is the meaning of energy density in a capacitor? Energy we know, half CV square. What is energy density? See, energy is U, that is equal to half CV square. We know very well, for a parallel plate capacitor, C is equal to epsilon naught A by D. I hope you know this. For a parallel plate capacitor, C is equal to epsilon naught A by D. Also, we know by the relation between electric field and potential that V will be equal to E into distance D. This is the thing. So now if you put both of them here, that will become equal to half C. I'll write epsilon naught A by D, and V will be ED, like this, CV square. So epsilon naught A by D into ED square. So it will become equal to half epsilon naught A by D into E square D square, and that is called as 1 by 2. This D will get cancelled. You will get 1 by 2 epsilon naught A E square D. This area into this distance between them, the area into distance will become the volume, isn't it? So this energy per unit volume, that is A into D, that is known as energy density U bar. Remember this. What is energy density? That is energy stored in the capacitor per unit its volume. Volume, how we will get? By area multiplied by distance. That will be equal to how much? Half epsilon naught A square. Never forget this. Very important. Very, very, very important. And also, one more relation is there about the force, that will be equal to energy density into area of the plate. Remember this also. Energy density, when it is multiplied by the area of the plate, you will be getting the force on the plates. These two things. So what will be the unit of energy density? It will be equal to joule per meter cube. See, this concept, many students are leaving it in the examination, for the examination, but I have seen questions coming from this area also. Energy density is half epsilon naught A square, and force formula is energy density multiplied by the area of the plates. So if I go to the next part, that is a question. A parallel plate capacitor of plate area A has a charge Q. The force on each plate of the capacitor is how much? So if you have a parallel plate capacitor, its area is A and the charge is Q, the force is being asked. So again, I told you in the formula, from there only it has come. The force between the plate F can be found out. F will be equal to energy density into A. Now energy density is how much? Half epsilon naught A. So half epsilon naught, half epsilon naught E square, I think. E square into A. So you got the value of force as half epsilon naught E square A. Now, if you see here, What is electric field due to the charge plate? In last class we have seen, yesterday's class, E was sigma by A. Sigma by A the whole square into A. So how much you are getting the value of force? So force would be coming half into epsilon naught into sigma square by A square into A. So I am getting F is equal to half epsilon naught. Instead of sigma, I can write Q by A. So it will become Q square by A square, isn't it? So I think not sigma by A. Sorry. Electric field is equal to sigma by epsilon naught, isn't it? Electric field to the two charge plate between the center, it was sigma by epsilon naught. Sorry. So only by a single plate, it was sigma by 2 epsilon naught. But if you remember, if you have two charged plate with equal charge densities, one is negative and one is positive, between them we have found sigma by epsilon naught. So electric field was sigma by epsilon naught here. So I'm just writing it once again. This will be equal to half into epsilon naught sigma by epsilon naught the whole square into A. So then when I solve it, here I will have epsilon naught square. So here I have epsilon naught. Sorry, once again, I'll do one thing. I'll just write everything once again. Sorry. So I know the formula of F, which is equal to energy density into A. Energy density is equal to half epsilon naught E square into A. And between the plates, I know the value of E square is sigma by epsilon naught square into A. And then it will become half epsilon naught sigma square by epsilon naught square. This will get cancelled into A. So I am getting the force as half sigma square A by epsilon naught, and then sigma can be written as Q by A. So 1 by 2 Q square by A square epsilon naught into A. This will get cancelled. So finally you will get force is equal to Q square by 2 A epsilon naught. So Q square by 2 epsilon naught A. So see, if you know this thing, everything else you may just derive by the knowledge. I hope you have understood this question. Next, we are coming to we're reaching the last topics. So we have come to the common potential, the concept of common potential and loss of energy. So redistribution of charges, I will say. So when two capacitors are connected, when two capacitors, when they're connected and they have different charge or they have different potentials, what happens? No, there will be redistribution of charge. Charge will travel from one to another capacitor, and there will be a common potential coming. There will be a common potential coming, V dash we say, that is equal to C1 V1 plus C2 V2 by C1 plus C2. Remember this. This is the formula of common potential. And what is observed, please pay attention here, that energy, total energy of the capacitance before the combination and total energy of the capacitance after the combination was not same. So before the combination it has some energy, after the combination energy reduces. So that we came to conclusion that energy must be lost, and that's how the loss of energy was found. It is lost in terms of heat or some other energies. So that initial energy minus final energy, ui minus uf, is also you should remember, and that is equal to C1 C2 into V1 minus V2 the whole square by 2 C1 plus C2. This is the formula of what is the energy lost, delta U. Delta U, that is equal to initial energy minus final energy, because initially it was more and after they were connected energy was reduced. So what is the energy lost? C1 C2 into V minus V2 the whole square by 2 C1 plus C2. See, all these things, derivations are there. If I start doing it now, it will take the whole class. 1 hour it will take for deriving itself properly. So these things you should remember, because direct questions are coming from these areas. So if I go to one question based upon this, see, common potential question is there. So a capacitor of capacitance C1 is charged up to potential V and then connected in a parallel to an uncharged capacitor of capacitance C2. The final potential difference across each capacitors will be how much? So they're asking you the common potential V dash, and we know the formula of V dash, that is equal to C1 V1 plus C2 V2 by C1 plus C2. So in this case, what they have given? They have given that first capacitor is charged up to potential V. That is V1 is given as V. And second potential is uncharged. So V2 is given as 0. When I put that, V dash will become equal to C1V by C1 plus C2. See, direct question. Just by knowing the formula of common potential, you got the answer. C1V by C1 plus C2. If you're not knowing the formula, gone. You cannot. Next is about polar and non-polar molecules. Actually, we have come to the concept of dielectrics and the capacitor with dielectric medium. So polar and non-polar molecules, see, they are two different kinds of molecules. If it is a polar molecule, no, then their centers of positive and negative charge. Polar molecules are those, they are those whose center of positive and negative charge will not coincide. So suppose I have some things like HCl. If you take example of hydrochloric acid, the positive of the hydrogen and the total negative of chlorine, they will not be in a straight line. They will not be identical. It will have some bend. So in a simple way, if I say the polar molecules are those molecules whose center of positive charge does not, whose center of positive charge does not coincide with center of negative charge. If it coincides, it is called as polar molecules, as simple as it is. So if the centers are not coinciding, they will be called as polar molecules. If they are coinciding, they will be called as non-polar molecules. Some examples I told: HCl, HNO3. These are the examples of polar molecules, and non-polar molecules can be nitrogen and all these things. So getting late actually. So if I come to parallel plate capacitor with a dielectric. So if I have a parallel plate capacitor and if you introduce a dielectric between them, then what is the new capacitance? This question is also very common in the examination. Suppose I have a capacitor like this, and in between, if I am introducing some capacitor of dielectric constant K and having a thickness of T, and obviously distance between the plates are D. So what is the new capacitance? We know very well that capacitance will be equal to epsilon naught A divided by D minus T plus T by K. So as simple as it is, the capacitance, the new capacitance when the dielectric is introduced is epsilon naught A by D minus T plus T by K. K is the dielectric constant. So see, if you have T equal to D, that is, if I have the thickness completely in this dielectric, fully occupied, then what will happen? T minus D means this will get D minus D will become 0. C will become equal to epsilon naught A by D, and K will go above. Same formula of parallel plate capacitor, epsilon naught A by D. And obviously, if you have a dielectric introduced, it will be multiplied by dielectric constant. You know very well. So it's a simple thing. But this formula, if you remember, all the cases of parallel plate capacitor can be solved. So let us see one, last question this is, and this is purely based upon the passage type question this is. So once again, a probable question in the examination. A dielectric slab is a substance. One passage was given about this, and the question is something like that. The question is, in a parallel plate capacitor, the capacitance increases from 4 farad to 80 farad, okay, on introducing a dielectric medium between the plates. What is the dielectric constant? So, okay, that is a simple question. So, initially the capacitance was 4 farad, then it became 80 farad. They're asking what is the capacitance. So, what is the dielectric constant? They're asking you K. So, obviously, what is the capacitance with dielectric? That is with dielectric, that will be equal to K times the capacitance without dielectric, isn't it? That's what we know. We know that C is equal to epsilon naught A by D, and we know C dash is equal to epsilon naught A K into D, K by D, isn't it? So we can see very clearly from this expression itself that the new capacitance with dielectric will be K times the old capacitance. So K can be found very easily from here. K will be equal to what? K will be equal to C dash by C with dielectric, without dielectric. So what is C dash? 80 by 4, and that will be equal to 20. So the electric constant must be equal to 20. Once again, the concept, very simple concept, that C, which was equal to epsilon naught A by D, C dash, which is equal to epsilon naught A by D into K. We can see very clearly from here that C dash is K times C. So K will be equal to C dash by C, and you get the answer directly. Simple question. So next question of the same passage type. A parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. The separation between the plates is now reduced to half, and the space between them is filled with a medium of dielectric constant 5. So they have given K is equal to 5, isn't it? And they have given that capacitance initially was equal to 8 picofarad. Pico is 10 to the power minus 12 for your knowledge. Okay, anyhow. And the separation between the plate is now half. So D dash has become D by 2. And the space between them is filled with this K, and calculate the value of capacitance in the second case. So now you have to find the value of capacitance. We know very well the formula of capacitance. That is C dash is equal to epsilon naught A by D into K, isn't it? So D has become D by 2. That is D dash here in this case. It became D by 2 and K is here. So when you see, you'll come to know epsilon naught A by D is given, isn't it? And above you have to multiply by 2K. So initially it was 8 picofarad. So 8 into 2 into K is how much? 5. So it will be 80 picofarad. As simple as it is. 80 picofarad is the answer of this question. And then you have the next one, a dielectric introduced between the plates of parallel plate condenser. So we know very well why we are introducing dielectric. In a capacitor, dielectric is introduced to increase its capacitance. What is there in that? So obviously to increase the capacity of the condenser. That is the whole aim. Why we are introducing the dielectric inside the capacitor? To increase its capacitance. So I think the last one, the parallel plate capacitor of capacitance 1 picofarad has a separation between the plate as D. When the distance of separation becomes 2D and wax of dielectric constant X is inserted in the capacitance in it, then the capacitance becomes 2 picofarad. What is the value of X? So they have told, see, previously there was a capacitance with a capacitor with a capacitance of 1 picofarad, and it has a separation of D. When the distance of separation becomes 2D, so now we are having it as 2D, and a wax of dielectric X is inserted. So we have some dielectric inside, and they have given the value of K as X. But they have given the value of C dash as 2 picofarad. They are asking you what is the value of X. So once again I have told you the simple thing, C dash, C formula is equal to epsilon naught A by D, isn't it? And C dash will be equal to epsilon naught A by D dash into, because area is not changing, only D is changing, into K. So epsilon naught A by D dash will become 2 times of D into K. So C dash will become equal to, we know epsilon naught A by D is equal to C, that is 1 multiplied by K. K value is X, we want to find that, by 2, isn't it? So C dash is given as 2 once again. So C dash is 2, 2 is equal to X by 2, so X is equal to 4. So any of option, this is option 4. So see how simply you can found. So again I am repeating, you need to just remember the concepts, you need to just remember the formula as well as the concepts, and then only you can do very well in the examinations. So it's simple, this chapter, both chapters what we have seen from last 2 classes, last 2 days, that is about the electric field and charges and about the electric charges and capacitance. It's not that tough, but the only thing is you need to remember all the concepts and you need to remember all the formula. If these 2 things you are remembering correctly, no one can stop you from scoring marks. Believe me, it is not that tough. Only thing is all the formula, all the concepts should be there in your head when you're going for the examination. I hope this session was useful for you, and we will meet once again tomorrow in the evening to learn the third chapter of physics, current electricity. Till then, take care. Bye bye. And if you have liked this video, please like it and subscribe to our channel. Take care. Bye bye.